Okay, welcome ladies and gents to your PN43 notes, which is all about de Moivre's theorem and the nth roots. Now, by the way, de Moivre is French, so that R is very soft at the end. It's very hard to say, so if I keep slurring it, it's because I'm trying to sound very French. Anyway, let's first take a step back to the good old days when we would talk about complex numbers. Remember, when we do have them, the first part of a complex number is the real part, where the second part, of course, is the imaginary. So before we even get into any kind of theorems, we just need to take and make sure you understand how to plot points on what we would call the complex plane. And if you look at this image right here, and I'm going to try to enlarge it. Notice that what we have here is a real axis and an imaginary number axis. And when we try to plot a point a plus ba, we can plot it right on that axis. So rather than doing something as general as that top one, let's just talk about this one right here. Notice here we have that real axis and an imaginary axis, and we have the number 2 plus 3i. So notice that we went over 2 and then up 3 to 3i, and that right there is where we would plot that point. I'm going to erase that so it's not in the way, because what I do want to do is just talk about how, this is kind of tying in with why it is even in this chapter, or the chapter we just got finished, is that if you talk about making a nice little right triangle, again where this is 2, and we know this is the I-axis, so I'm just going to put 3 here. And if we find that hypotenuse or the radius or the magnitude or all the stuff that we've been doing lately using the Pythagorean theorem, 2 squared plus 3 squared equals, I'm going to actually call it r squared, the radius. And if we do that, we end up with the square root of 13. And I'm bringing that up just because it helps us as we move forward here down below. So a couple of things here. You just need to be able to plot a point that has an imaginary and a real part on a complex plane. So if you look up here, these are our objectives, and that's the very first thing we are doing, is just making sure you understand what a complex plane looks like. So here it says plot u equals 1 plus 3i and v equals 2 minus I, and then also plot the composite, or the, not composite, I'm sorry, the sum of those two numbers. So the first thing is that we can clearly plot 1 plus 3i, and I'm going to really make this much bigger because I'm going to have a hard time seeing this here. 1, 2, 3i, here we go. And I'm going to just say again that this is the real axis. Oof, this is the imaginary. Okay, so that point right there is the u point. Then we have 2, negative 1. That's going to be right here, which is the v point. And then if you add those together, 1 plus 3i, so the u point, plus the v point, which is 2 minus I, that would mean that your u plus v point is 3 plus 2i. So I'm going to plot 1, 2, 3, up to, and this right here is the sum. Pretty straightforward, right? Not too difficult. So that's just kind of plotting complex numbers and showing that you can do some addition of numbers on the complex number plane. Okay, so now we get into a little bit more of the the more complicated stuff here. It says right here, notice again, tying in with everything we've been doing, that if you have this complex number right there, a plus bi, that the horizontal movement is going to be r cosine theta, and the b movement up is going to be the r sine theta. That should look very, very familiar with the components of vectors or switching over from polar to rectangular coordinates, all that kind of good stuff. And notice we still do have just a radius there. So Why is this important? Well, if we want to switch from complex form to trig form or vice versa, we need to use that information. Just kind of like we switch from rectangular to polar and polar to rectangular. Now we just need to be comfortable switching from complex number over to trig form, or again vice versa. And what we do want to use, and I don't know how well you can see this up in that box up there, but you're going to either use z is equal to r cosine theta plus ir sine theta, or here's the one I tend to like, r cosine theta plus I sine theta. And you know what, again, it all stems with what we've been doing. So let me just kind of take a step back and kind of show you what I'm talking about. And you're going to probably say, where did that z come from? That z came from right here. We use that as our, to remember that it's not just the xy axes that we're talking about. So okay, so let's just get right into it, and I know you guys will pick it up. It's just kind of a little different though. So this point right here, if I plot that point, I'm going to do that because I think it's really important to see where it's at. You have 1, and then if you think about going over, you know what, I'm going to make this a little bit easier, bigger for me. This is length of 1 going down, because it's negative, square root of 3. So we're going 1 on the real axis down, square root of 3. Actually, I'm going to put a negative square root of 3 on the imaginary axis. If we create a right triangle to that point and use Pythagorean theorem to find the hypotenuse, or you could really recognize that, I don't know if you see this, but very quickly, if you have a 1 here and a square root of 3 over there, this, using Pythagorean theorem or not, is going to give you 2. And that is, I know that instantly because this is a 30, 60, 90 degree triangle. Now, if you were to calculate this using SOHCAHTOA, you would find that this angle right here is 60 degrees. And if you're not comfortable saying that that's 60 degrees just by special triangles, special triangles are so powerful, you could definitely use your SOHCAHTOA and you'll get that answer as well. Or unit circle, right? Because we can kind of use that same idea of multiplying values and so on. Anyway, okay. So here we go. I know that 30 degrees, if we talk just about the directional, let me kind of change colors here, we are talking about going all the way around here, so that is 300 degrees, or you could use negative 60 degrees. And I do want to say that over here we're in degrees, but notice what they're saying here, that the trig form has to be from 0 to 2 pi, so we really need to switch that 300 degrees or the negative 60 degrees into radians. And I'm going to stick with the 300 degrees. We know that if we're coming all the way around, we're talking about, if there's 60 degrees there, we're talking about an over 3, and it's going to be a 5 pi over 3. So you can convert that manually, or I know many of you would probably know that really quick in your heads. But, okay, so we haven't done anything really new here. We're just kind of making sure we have our angles. Using Pythagorean theorem, we found the radius, and now we can use the formula up there to now switch our complex number 1 minus square root of 3i over into a into trig form. So here's what we do. We go z equals, and whether you use the first equation or second one doesn't matter, but I know my radius, and I'll put that up here, was the hypotenuse, which was 2, so I'm going to put 2 in parentheses cosine, and the theta, again, was our direction angle, but of course it had to be in radians because of the notation saying it has to be between 0 and 2 pi. So I have cosine of 5 pi over 3 plus I sine of 5 pi over 3. And again, all I'm doing is really following this formula, if you will. So now I'm going to simplify it. And, well, actually, what am I saying? No, of course I'm not going to simplify it, because otherwise I'll get right back down to my complex number. I'm just like going in a complete circle. So that is it, folks. I'm sorry, it seemed a little anticlimactic there for a minute, but all you're doing is switching this form and putting it into trig form, and this is the trig form. So if you notice that all you're really doing is making sure that you know what the radius is, or the hypotenuse, and the direction angle. And you know what? That's it. That's all you do. Okay, so now let's talk about letter B, and I am going to try using this thing that someone showed me and see if I can shrink this whole thing that I just did, because I made it awfully big. There we go. Look at this. Kind of put it over there, out of my way. Okay, I want to now focus on this one right. Oops, I switched over. This one right here. So -3 minus 4i. So again, you can't do this without graphing it, folks. So if you're really not wanting to do the graphing, it doesn't make it any easier here. So I'm going over -3 here. I go 1, 2, 3, and then I'm going down 4. -4, and again I don't put the I because I know this is the I coordinate, or axis. So we have the real axis and the I did the square root, sorry, I'm talking and writing the wrong thing here. -4. So I know this is -3, and I know it's -4i because that's the imaginary axis, is what I was just trying to get across. Now if you use Pythagorean theorem here, or notice that's a 3, 4, 5 triangle, that makes it a little bit easier. And now, again, we're going to need to find this angle right in here, right there. Actually, let me switch colors so you can really see it. Actually, I'll do a green dot right there. So I'm going to go tan of that angle, we'll call theta, equals the opposite side over the over the adjacent side, sorry. And when we do inverse tan on this, this is not a nice angle by any means. And make sure, because again we're doing radians, make sure you're in radian measure here. So switch your mode in your calculator to radians. Excuse me. So when you do the inverse tan, you end up with a radians of 0.927. Now that's just that green angle, but remember, we need a directional angle. I'm going to use purple here. We're going to go from here all the way around to here. So we have the green angle already, but we have to add on pi radians. So if you just calculate this out, because it's not pretty by any means, our direction angle is going to be 4.069 radians. So now we have our direction angle, we have our radius is equal to 5 right there, and now you know what? You just throw it into that formula. And I'm going to shrink this so I can finish it up. So z is equal to the radius, and you know what, just for fun, just to kind of shake it up a bit, I'm going to use the first one now, just to show you it really doesn't make a difference. So radius is equal to, I just lost it, 5 times cosine of 4.069 plus the radius, and it says I radius. If you go radius I, that's fine as well. So I like writing it like this just because who I am. And then sine of, I'm losing 4.069. Oops, 9. And you know what? That big old ugly thing is the trig form of that complex number. Okay, so let's kind of now look at the back of this note guide and see if we can go in reverse. So if you look at this, it says, okay, we have a complex number, or excuse me, we have the trig form of a complex number, but I want to write it like that. So just like before, we need to know our radius, and we need to know our direction angle. And I'm just going to say that, notice that we're in degrees, and you do need to switch it, or I don't know, it doesn't really matter whether you're in, I suppose, degrees or not, but the point is that I find I find radians to be easier in these problems. So I'm going to say 210, I'm going to switch this over to radians, 210 over 1 times pi over 180 degrees. And when I simplify this, it ends up giving me 7 pi over 6. So that lets me know very quickly that I'm going to be right here, that point right there. And so that point right there is going to be negative square root of 3 over 2 and negative 1/2 on the unit circle. So this is going to tell you whether or not you're kind of how much you've been liking radians, because when I hear a radian, I can tell the point on the unit circle really quick, but when I hear 210 degrees, I don't think of it as quickly. So okay, so now what I'm going to do is I'm going to go, okay, so 8 times the cosine of 210 degrees is negative square root of 3 over 2, using the unit circle, no calculator of course, plus I times negative 1/2, which I would have put that the other way myself. And then I'm going to distribute that 8 through. And so 8 times negative square root of 3 over 2 is 4 square root of 3. And if you really have trouble with those fractions, put it off to the side. 8 over 1 times square root of 3 over 2, or negative square root of 3 over 2. Notice you've got these simplification that's happening, and you just can multiply it right across. So we have negative 4 square root of 3, and then again 8 times 1/2 is going to be 4, so it's going to be minus 4i. And that, my fine young ladies and gents, is the imaginary number if the trig form looks like that. Now there's this beautiful proof down here that, you know what, we're just not going to do, because we want to get right into this de Moivre's theorem, which I have been promising. So it says let z, so I'm going to read this right now. It says let z equal r times the quantity cosine theta plus I sine theta, recognize that I'm sure, and let n be the positive integer. If that's the case, so if this is the whole reason why we need to get used to this, because now if we have z to the nth power, any power n, we could, instead of expanding out, we can just use these formulas, one or the other, doesn't matter which, to simplify it. And hopefully here in a couple minutes you're going to be like, okay, I see the power in this. But let me just start at the beginning. First of all, this thing right here, this 1 plus I square root of 3 quantity cubed, we could expand this out going 1 plus I square root of 3 times 1 plus I square root of 3 times 1 plus I square root of 3, simplify it, and you would eventually get your answer, or you could just use de Moivre's theorem and do it very, very quickly. Now, I think this one with the third power isn't as exciting as if you do like to the 8th power, because can you imagine multiplying those those complex numbers together times itself 8 times? It's crazy. So here's how we do it. We first look at the power of this complex number, which in this case is 3. So I'm going to write n equals 3 here so I don't forget that. And then what I'm going to do is I'm going to graph my complex number, just the complex number, not the cubed. So I'm going to go over 1 and up square root of 3. Oops, I don't want to do that. Well, actually I do want to do that. What am I thinking? Okay, there we go. And we have one leg that's 1, the other length is square root of 3, and again you could use Pythagorean theorem or recognize it from the front page and what I talked about before, which is a special triangle. This, I'm going to switch colors, angle right in here, if you use tangent, is going to give you 60 degrees, or if you can just recognize that as a special triangle, again, that works out really, really very, very handy. So that's 60 degrees right in there. So what I have here is a radius of 2 and a theta, a rotational direction angle of 60 degrees. Okay, because we all know that with all of this, you notice you keep going radius and direction angle over and over and over again, and that's really consistent with what we've been doing throughout this whole chapter. Okay, so now let's use this formula right here. So it says z cubed, so we're talking about cube because we have a 3 right there, equals, And again, it doesn't matter which one you use. I'm going to use the second one just because it's my preference. The radius, r, which is 2 cubed times the cosine of n, and again remember n is over here, n equals 3, times the direction angle of 60, plus, oh, this is where I'm going to do that little cut thing to make it just a little bit smaller so I can just move the thing here. Okay. I lost my train of thought here. Where am I at? Plus I sine of 3 times 60. Now, okay, so now we simplify it a little bit. Okay, so we have z cubed. So this imaginary number cubed is equal to 2 cubed, which is 8, times the cosine of 180 degrees plus I sine of, and this is not 360 degrees, it's 3 times 60, which again is sine of 180 degrees. Okay, so we're just simplifying here. Now, z cubed equals 8. If you think about cosine at 180, which is right here, that's going to be -1 plus I times the sine of 180. Right there is going to be 0. And you know what's beautiful about this is you end up with 8 times -1, because 0 times I is 0. And we end up with -1. And so we know that this number cubed is going to give me -8. That is so cool. So while it doesn't look like we saved any time, keep in mind that if we had to do these long-handed, especially if your n value is like 20 or 25 or some huge number, you obviously wouldn't want to have to do that all long-handed. So there's going to be questions on this. It's a little weird initially, and we'll address those in class, obviously. But what I want you to do is start them right here, this page 559, 1 through 18 all, 31 through 38. And you know what? You will find that this is a very cool thing. It just, again, takes a little bit of time getting used to. Okay, thank you for tuning in.